In this video, we will go over the basics of normal distribution. Normal distribution is also called a Gaussian distribution. It is the most important and widely used distribution in statistics. Many populations have distributions that can be fit using normal distribution. Here are some examples: the height of the population, scores of a test, returns of the stock market, income of the population. Now next, let's get to the math of normal distribution. A continuous random variable x has a normal distribution with the parameter mu and sigma if its density function is given by fx is equal to 1 over square root of 2 pi times sigma e to the negative x minus mu square divided by 2 sigma square. X is any real value. We typically use the notation n mu sigma square to represent a normal distribution with the parameter mu and sigma. Now here are some properties of the density function fx. fx is symmetric about the line x equals mu. The second property, the expected value of x is mu. The variance of x is sigma square, or the standard deviation of x is sigma. So the calculation of this is a bit complicated. We will not cover the calculation in this video, but we just need to remember that in this density function, mu is actually the mean of the random variable x. Sigma square is the variance, or the sigma is the standard deviation. The next property, a larger sigma implies a more spread out density. A smaller sigma implies a more peaked density. Now let's look at some examples. There are 4 curves here corresponding to different mu and sigma. The first one, the blue curve, mu equals 0, sigma square equals 0.2. You can see the blue curve, the blue density curve is symmetric around the line x equals 0. And because the sigma square is small, so you can see the curve is very peaked. Now the second is the red curve, mu equals 0, sigma square equals 1. And you can see again it's symmetric around the line x equals 0, sigma is 1, so it's not very peaked compared with the first one. The next one, mu equals 0, sigma square equals 5. The yellow curve here, and you can see because the sigma is larger, so it's more spread out. Again, it's symmetrical about the line x equals 0. The last one, mu is equal to negative 2, sigma square is equal to 0.5. So because mu is equal to negative 2, the green curve, you can see the green curve here, it's symmetric around the line. Mu is equal, x is equal to negative 2. Next, we're going to introduce the standard normal distribution. The normal distribution with the parameters mu equals 0 and the sigma square is equal to 1 is called standard normal distribution. We typically use the notation z to represent a standard normal random variable. The PDF is given by phi of x is equal to 1 over square root of 2 pi e to the negative x squared divided by 2. Typically, we use a lowercase phi of x to represent the PDF of a standard normal. The CDF is given by probability z. Recall that z is, we typically use z to represent a standard normal random variable. The probability z is less than lowercase z is equal to this integral, where the phi is the PDF of a standard normal. Typically, we use uppercase phi of z to represent the CDF of a standard normal distribution. So this notation will be used very often. Now let's talk about the properties of a standard normal. The standard normal density function is symmetric about the y-axis. It is often used as a reference distribution from which information about other normal distributions can be derived. The CDF of a standard normal distribution can be calculated with a simple function in R or MATLAB. We're going to show you some examples later. Now here are some examples of a standard normal distribution calculations. The first one, again, we assume Z is a standard normal random variable. The first one, probability Z is greater than 1.5. So this is equal to 1 minus probability Z is less than or equal to 1.5. This is because Z is less than or 1.5, less than or equal to 1.5 is the complement of Z is greater than 1.5. So the probability should be 1 minus. Okay, this is equal to 1 minus phi 1.5. Recall that a phi is the notation we use for the distribution function of a standard normal. So now to calculate this phi, we can use the function p norm in R. So let's do the calculation. So first let's open R. So we can use the p norm function. So this is 1 minus p norm 1.5. And again, we use the function p norm here in R to calculate the function phi. So this is equal to 0.067 roughly. This is equal to Okay, let's look at the next example. We want to calculate the probability Z is between negative 0.8 and 1.5. This is equal to the probability Z is less than or equal to 1.5 subtract probability Z is less than negative 0.8. And because we are trying to calculate the Z between these two numbers, we first calculate the probability Z is all the way up to 1.5. Then we subtract the probability Z is all the way up to negative 0.8. What we are left with is the probability of Z is between these two numbers. And recall that Z is a continuous random variable, so less than the probability that Z is less than negative 0.8 is the same as Z is less than or equal to negative 0.8. Now this is equal to phi of 1.5 subtract phi of negative 0.8. Now again, we can calculate this using R. Let's open RStudio. P norm 1.5 subtract P norm negative 0.8. And this is equal to 0.72. So this is equal to 0.72. Now we can also visualize the calculation in this graph. Now this curve is the density curve of a standard normal. Now the probability of Z is between these two numbers, negative 0.8 and 1.5, is the area under this curve between these two numbers. Now, if you look at the first item here, the probability Z is less than or equal to 1.5 is the area all the way up to 1.5, or the combination of this red area and the blue area. The second part of this calculation, probability Z is less than negative 0.8 is the area that's all the way up to negative 0.8, or this red area. So if you take the difference, it's this blue area, right? So this is the visualization of this calculation. Now let's look at the next example. In this example, we want to prove that the probability Z is greater than or equal to 1.5 is equal to probability Z is less than or equal to negative 1.5. This is actually pretty obvious because the density function of Z is symmetric about 0. So you can see from here, is symmetric around 0. And the left-hand side, the probability z is greater than 1.5 is the area under this curve, and it's on the right-hand side of 1.5, or this area here. And this side, the probability z is less than or equal to negative 1.5 is the area under this curve on the left-hand side of negative 1.5, and all this area plotted here. And you can see because the density curve is symmetric, so these two areas are the same. And you can see here that this 1.5 is nothing special. You can replace this with any number. It's still true because of this, because the curve is symmetric. Now let's look at the next example. In this example, we want to calculate the probability z is between negative 1 and positive 1. So this is equal to probability z is less than or equal to 1, subtract probability z is less than negative 1. This is equal to phi of 1 subtract phi of negative 1. And this is equal to 68%, roughly. Now, in the next video, we're going to show that given any random variable x, which is normal distribution with the parameter mu and sigma, x minus mu divided by sigma, or x minus its mean divided by its standard deviation is going to be a standard normal. So now based on what we just proved, we have the probability negative 1 less than or equal to x minus mu divided by sigma less than or equal to 1 is equal to 68%. So in other words, because x minus mu divided by sigma is a standard normal, so we just showed that the probability a standard normal is between negative 1 and positive 1 is 68%. Now this can be also written as the probability x is less than or equal to mu plus sigma greater than or equal to mu minus sigma. This is also equal to 68%. So this means the probability that x is within one standard deviation of the mean is 68%. We can also illustrate this in a graph. This is a density function of a normal distribution with the parameter mu and sigma. And this is mu minus sigma, this is mu plus sigma. The area of this part, of this here under this curve, between these two numbers is roughly 68%. Next, we want to calculate the probability z is between negative 2 and positive 2. And this is equal to probability z is less than or equal to 2, subtract probability z is less than negative 2. And this is equal to phi of 2 subtract phi of negative 2. And this is roughly equal to 95%. Using the same argument as the previous example, if x is a normal distribution with the parameter mu and sigma, then we have the probability x is between mu plus 2 sigma and mu minus 2 sigma is equal to 95%. In other words, if x is a normal distribution, then the probability that x is within 2 standard deviation of the mean is 95%. Now let's look at one more example. In practice, sometimes we want to find an a such that the probability z is less than or equal to a is equal to a particular number, say 0.9. So how do we find this a? Now, p z is less than or equal to a is equal to phi of a, and we want to find a such that this is equal to 0.9. So a should be equal to phi inverse 0.9. The phi inverse here is the inverse function of the CDF of a standard normal. Now how do we calculate this? We can calculate this using our function called a Q norm. Let's do the calculation here. Q norm 0.9 is equal to 1.28. So this is equal to 1.28. So remember, we use the Q norm functions in R. Okay, thank you for watching.